Module 5. In this module, we are studying a two-reaction theory or a theory of a salient pole machine. Then V goes for the synchronous machine, the parallel option of a generator, necessity of the parallel operation, conditions and load sharing that we are studying. Also, we are studying what are the different methods of connecting the two or more number of alternators in parallel. That also we are seeing in the form of synchronization. Then the stiffness of the machine that we are studying with the help of a synchronizing power and determination of x and x cube using a slip test for salient pole machine also we are studying in this particular module. In last section that we are seeing the capability goals of the alternators and the hunting and the importance of the damper winding to minimize the hunting. These are the things we are studying in this particular module. Then we start with the two reaction theory. We know that in the case of a non-salient pole type of machine or a cylindrical rotor type of machine, the air gap, that is the gap between the stator and rotor, is uniform. Therefore, the distribution of the MMF in the air gap is uniform. Because of that, the reactance, the offered or the reluctance is the uniform throughout the air gap. Either you can take a pole axis or interpolar axis, the air gap is uniform. Because of that, the reactance, the offered throughout the air gap remains same for the armature reaction. That we'll see now. That is, in the cylindrical, same thing it is written here. In a cylindrical rotor, the air gap is uniform, hence the effect of MMF will be the same whether it is along the pole axis that we are calling subsequently D axis and interpolar axis. The gap is uniform. Hence, the reactance of the stator is same throughout and hence it is called as a synchronous reactance. That is, you can see the figure here, that is air gap as the uniform throughout, hence the MMF distribution in the air gap is uniform, at the same time the reactance is same whether it is along the pole axis, that is this is the pole axis, therefore it is called as D axis, and it is interpolar axis. Here also the air gap is uniform. However, in the case of the salient pole type of machine, in the case of salient polar type of machine, we look into what is the difference between the non-salient and salient. Here the air gap is not uniform throughout. Along the pole axis, air gap is small, whereas in the interpolar axis it is large. Therefore, the distribution of the MMF in the air gap is not uniform. Hence, the reactance along the pole axis, that is here afterwards we are calling as the D axis, and the reactance offered along the Q axis not a same. That we are explaining here. That is, in the case of salient pole of machine, the air gap is non-uniform. It is smaller along the pole axis, that is the gap is smaller along the pole axis and is large along the interpolar axis. Hence, the axis now they are called as direct axis or a D axis in short, and quadrant axis or in short it is called as Q axis. That is, the pole axis is called as a D axis, interpolar axis is called as a Q axis. Hence, the effect of MMF when acting along the direct axis will different than that when it is acting along the quadrature. It is quite evident because the air gap is not uniform. Because of that, the distribution of the MMF along the D axis and Q axis is not uniform. Hence, if the MMF is different, hence the reactance of the stator cannot be same when MMF is acting along D axis and Q axis. Because of non-uniformity of the air gap and non-uniformity of the distribution of the MMF, the reactance along the d-axis and reactance along the q-axis are different. That I am showing here. You can see here, this is the pole. I am considering here two-pole machine. It is a d-axis. All along the poles, it is called as a d-axis, and it is an interpolar axis. It is an interpolar axis, or it is also called as q-axis. The pole axis is called as d-axis. Then one more thing, we know that is the main flux is acting along the d-axis. The main flux is acting along the main fluxes. That I am explaining here. That is, the main flux is acting along the d-axis. At the same time, we know that the induced voltage, because of the main flux, lags the main flux by an angle of 90 degree. That we are also aware of it. That is, the induced voltage always lags the flux by an angle of 90 degree. Here it is the main flux or MMF, and the corresponding the induced voltage is lagging thus by an angle of 90 degree. Means what I mean is the generated voltage is all along the q axis. Then I am connecting the alternator to a lagging load, means the current which is delivered to the load is lagging in the nature. Therefore, I am drawing here the current which is lagging the voltage by an angle of phi. Then, because of there is a current is flowing in the any conductor or a winding, then it is producing its own MMF. It is producing its own MMF, that is represented as FAR, where FAR is the armature flux produced by the armature current. Then this FAR I am resolving into two components, one along the q axis, the another along the q axis. That is, one is FAD, the another one is FAQ. That is, I am resolving this FAR into two components, FAQ and FAD. Then we know that whenever there is a MMF is there, unlike in the case of your the electric circuit, whenever there is a EMF, there is a current is flowing. Hence, because of the MMF, there is a flux is producing. Therefore, because of FAQ, there is the flux is producing phi q. Just like it, because of a voltage, there is a current. Here, it is a magnetic circuit. Because of MMF, it is FAQ, it is a phi q is producing. Similarly, there is a FAD, that is a MF along the d-axis producing the direct axis, the flux phi t. Means, because of the armature current, there is an armature flux, armature MMF is producing. Because of the armature MMF, it has got two components I am resolving, FAQ and FAD. Because of FAQ, there is a phi q. Because of FAD, I have got a phi t. Then, we know that whenever there is a flux is producing, they are producing their own EMF. Because of phi q, there is a EAQ, and because of phi d, that is EAD. There is a voltage because of phi q is EAQ, that is armature EMF, what I am calling here afterwards. That is, because of phi q, there is a voltage EAQ. Because of phi d, there is a voltage is EAD. Okay, that I am explaining here. That is, it is a main MMF that I am showing here. Because of a main flux, there is an induced voltage that I have shown previously. Then, if the lagging power factor load is connected to the alternator, that also I shown. The current IA lags behind the generator by E by an angle of phi. Then, the armature current produces the armature flux. Ultimately, we are coming to FER. That is, you are seeing that all these events. That is, there is a main flux because of main flux E, and it is connected to lagging load. Therefore, it is current I is lagging E. Then because of I, FER. Now I am removing E and IM for the other factors. Then FER can be resolved into two components. Because of these two components, there are two fluxes are producing, phi q and phi t. Then the armature current produces a MMF of FER. Then armature EMF FAR is resolved into two components, that is namely FAD and FAQ. And if phi d and phi q are direct axis and quadrature axis fluxes respectively, what I am getting is phi q and phi d because of FAQ and FAD. These phi d and phi q are the flux which they are producing the voltage. That will come back. Unlike in your electrical circuit, we have got in the magnetic circuit there is a reluctance. The reluctance is along the d axis and reluctance along the q axis for the magnetic field. Just like it is equivalent to resistance in the case of electrical circuit. If you are analogy, if you are making electrical circuit and magnetic circuit, Rd and Iq are the direct axis and quadrature axis reluctances. Then we know that MMF is equal to just like EMF. How we are writing EMF? The EMF, just I will show you. That is, we know that E is equal to, that is, you can call I into R. Unlike in the electrical circuit, we have what? MMF is equal to flux into reluctance. Is it not? Therefore, the flux phi is equal to MMF divided by reluctance. The same thing I am writing here, that is the flux is equal to, it is FAD is MMF divided by the reluctance. Okay. Okay. Now, phi d is MMF in the direct axis divided by the corresponding reluctance in the d axis. Similarly, the flux in the q axis is equal to MMF of the q axis, that is FAQ divided by reluctance of the q axis. Therefore, we know that Rd, that is the reluctance along the d axis, is less than the reluctance along the q axis. Why it is so? Reluctance is less in the d axis because the air gap is small, therefore reluctance is less. Whereas in the interpolar axis or in the q axis, the air gap is large, therefore reluctance is more. Therefore, reluctance in the q axis is more than the reluctance along the d axis. Definitely, if the Rd is less, then ultimately phi d is more. If the Rd is less, then phi d is more. And the Rq is large, because of that phi q is less. Means ultimately we come to the conclusion that the flux produced by the armature current along the d axis is more as compared to the q axis. Therefore, I will write, because of the phi d, I have got the voltage EAD. That is, EAD and EAQ are the direct axis and quadrature axis armature reaction voltages respectively. Just have to look into the sequence of events. Because of FAR, FAQ, FAD, because of FAD, we have got phi d and phi q. Because of the phi d, we have got EAD and EAQ. That is because of the flux, we have got a EMF, EAD and EAQ are the direct axis and quadrature axis armature reaction voltages separately, respectively. Then, how we are writing EAD and EAQ in the form of the voltage, current and the reactance? That is, EAD can be written as the current along the d axis multiplied by the reactance along the d axis. Similarly, the voltage along the q axis can be written as the current along the q axis multiplied by the reactance. This XAQ and XAD are representing equivalent armature reaction effect along the d axis and q axis respectively. That is, XAD and XAQ represent the armature reactance along the d axis and q axis. Unlike, that is like our salient, non-salient pole type of machine, we have got a XA. That is a armature reactance. That is uniform throughout because the air gap is uniform. But here the air gap is not uniform, therefore you have got the armature reactance along the D axis is XAD, the armature reactance along the Q axis is XAQ. Therefore, how we are getting XAD? XAD is EAD divided by IAD. XAQ is equal to EAQ divided by IAQ. We know that the phi d is more, therefore EAD is more, therefore XAD is more. Just you have to look into. That is, EAD is because of phi d. Phi d is greater than phi q, therefore EAD is greater. Therefore, XAD is more because EAD is more than EAQ. Okay, therefore EAD by IAD gives the XAD and XAQ is given by EAQ divided by IAQ. This is how we have to find out armature reactance along the D axis and the Q axis. Therefore, we will come to the conclusion that XAD is greater than XAQ. XAD is greater than XAQ because here the EAD is greater than EAQ. Then we will see the vector diagram for the total process what I explained so far. That is a main flux. Because of the main flux, there is a induced voltage along the Q axis. Then lagging load I am considering because of IA, I have got a flux MMF FAR. This IA also can be resolved into IQ and ID, and this FAR is resolved into FAQ and FAD. Because of FAD, I have got phi Q and the phi D. This is the how we are representing to explain the two reaction theory. Because of phi D and phi Q, if you have got EAD and EAQ, then we are finding out XAD is equal to EAD divided by ID, whereas XAQ we are getting from EAQ because of XQ divided by IAQ, that is IQ. So that I am getting XAD and XAQ. Therefore, the total synchronous reactance along the D axis is represented by XD. It is a combination of XAD plus XL. That is armature reactance along the D axis plus leakage reactance, that gives XD, whereas XQ is equal to XAQ plus XL. And in the case of your non-salient pole type of machine, we know that is the generated voltage is equal to the terminal voltage plus IRA drop plus IAXS drop. Because in the case of non-salient pole type of machine, we have got only one reactance, that is synchronous reactance XS. These are all vector sum. But here you have got two reactances apart from the resistance. Therefore, your induced voltage will be the vector sum of the terminal voltage V plus IRA drop plus IDXD drop and IQXU drop. Then how to draw the vector diagram for this? First you have to draw the D axis and Q axis. Then your E should be all along the Q axis. Therefore, arbitrarily I am taking the voltage V, consider the lagging power factor I, then I am resolving this IA into two components, that is ID and IQ. Now, to V, what I have to add? IRA, that should be parallel to I. Just I am adding here IRA, which is parallel to I. Then to this IRA drop, what I have to add? I have to add IDXD. This IDXD should be perpendicular to ID because it has to lead the current by an angle of 90 degree. Therefore, I have to add here IDXD, which is perpendicular to ID. Then to the tip of IDXD, what I have to add? That is IQXQ, which is perpendicular to IQ, Therefore, I am adding here. Therefore, what we are getting is the total induced voltage E. This is how we have to draw the vector diagram for the alternator for two reaction theory or for the salient pole type of alternator.